Welcome to my talk about hacking World of Warcraft. My name is Greg Hoglund. I've worked on rootkit technology for a number of years, and in this particular talk I'm going to cover a rather specific application of Ring Zero technology used to inject code into the World of Warcraft game client. This may sound extreme, but it was a natural idea for me because I already had the capability to do stuff like this in my skill set, and it seemed like a really nice way to get around something known as the Warden client, which was an anti-cheater technology that was catching my cheating program. So, first of all, why games? It's kind of an interesting topic for Black Hat. I haven't seen anything like this before. First and foremost, it's really fun. I mean, actually, over the last few days, I've been talking to people about this talk, and I'm surprised at the number of people in here who play World of Warcraft. How many in here actually have a World of Warcraft account? Yeah, see, this is very popular. How many in here use botting or cheating programs? Be honest. In addition to it being fun, though, they're actually games are a really interesting experiment because the software is very complex. A program like World of Warcraft could be considered one of the most complex multi-user applications in the world. Another thing that's really cool is that there's actually a healthy community of game hackers, and they're not the same guys who come to this conference. Some of them are, there's some crossover, but there's actually a whole set of reverse engineers with a lot of really good skills that I happened to stumble into when I started playing around with these games. And I thought that was pretty neat, so hopefully there'll be some crosstalk. And last but not least, and probably the most important, is that gaming is a really big business. Microsoft says it's third only to web browsing and email on their platform. Now, obviously, the next question is why cheat at games? The first real reason is it's a challenge, right? You want to try to solve it. It's actually funner to write a cheating and a botting program for me than actually playing the game. But to be honest, I really suck at video games. How many here play Unreal Tournament? I have an aimbot for Unreal Tournament. I can be on the other side of the map with the sniper rifle doing headshots, and I'm still last in the frag list. So, it's fun to have an unfair advantage. To use the Unreal Tournament example, it's pretty obvious when you're aimbotting because these are impossible shots. So if you combine this with a six-pack of beer and some nice smack talking, you can have a pretty good night. With these World of Warcraft and other MMOs, though, there's actually another thing going on. There's actually a full economy in these games, and using cheating can make you money. So obviously, I don't really need to talk about what an MMO is. Basically, it's D&D and IRC mixed together. It's a geek's wet dream. The number of online games MMOs are doubling every 2 years, so they're tracking Moore's Law. There's over 50 active MMOs right now. IDG estimates that there's about 3 million players in the US. I think that number's probably a little low. And I don't know if you've seen the latest advertising on the Blizzard box, but it says 6.5 million players of World of Warcraft. That's a lot. Here's the statistics. You can see the number of players rapidly increasing here. Here's the total market share of the various MMOs. The big slice is obviously World of Warcraft. The kind of quarter of the pie down on the bottom is Lineage and Lineage 2, which is a very, very popular MMO, especially in Asia. So, people have figured out there's a real exchange rate, and you can actually go to a website and it'll tell you what the exchange rate between virtual in-game money and US dollars or euros is. Last year in 2005, over $600 million were traded in an aftermarket for virtual items that don't exist. I got a recent calculation from an economist that says you can make about $1.17 an hour playing WoW. That's not enough for us, but it's enough for some people in the world. Here's a site you're probably familiar with if you've ever bought World of Warcraft Gold before. This site sells it, and you can see the exchange rate's about 10 cents for one gold piece. Here is a chart showing the exchange rate over time in 2005, and you can see it settled down on about 10 cents per gold piece there. So in China, over 500,000 people play these games for the purposes of making money. They actually sleep on cots next to the computer. You might think this is a sweatshop, but you gotta understand in China or wherever this is, they choose this job. It's better than making shoes down the street, and it's better than working on Dad's farm. There is a video. I have a link here. My slides are not yet available, but when they come up, you'll be able to get it. This is a video that's a little a tour through a Chinese farming operation. And here's a couple of fellas right here working away. Now, let's talk about what the hackers are getting away with. There's one guy whose handle is Smooth Criminal. He specializes, or at the time specialized in writing exploits for games. Star Wars Galaxies was his target. Star Wars Galaxies, he made so much money duping gold, or I'm sorry, the in-game currency, I forget what it's called, but right. He actually had to go get, I think this is kind of an unconfirmed rumor, but IGE to go buy a whole bunch of accounts so that he could launder the money. He had so much of it. He made $1.5 million in 1 year, $700,000 of which he kept for himself. He bought a house, and in tribute, when you hit the doorbell, it plays the Star Wars theme song. Rich Thurman made 100 grand, farming about 9 billion gold. Interesting because he was using a server farm of about 30 machines. On eBay, you can see a single exploit sold for about $3,000. And some cheating sites, familiar with X Unleashed? That's a cheating site. I think they make around $40,000 a month. So cheating is big business. Just for fun, about 2 weeks ago, I purchased this exploit for you guys. This is a dupe bug for World of Warcraft. So supposedly you could duplicate an item, and the advertising said that it worked on the latest patch. I would doubt that it actually still works, but there it is. You stand outside of an instance, and then you party, and then somebody goes into the instance after you trade, and then he Hearthstone's back, and apparently you're supposed to duplicate the item. I couldn't get it to work, so I lost 20 bucks, but hey, I got a slide out of it. You'll notice it's downloaded as an executable. I had to run it in a VMware. I didn't even know what it did. So let's talk about cheating technology. We got an overview of the game. So what kinds of cheating is there? Now, I'm going to preface this with, this is not a complete treatment of all the different technologies. After talking with various people over the last couple of days, I've heard a lot of really interesting tricks and things that I am not covering in my slides. So forgive me for that. I put two categories of cheating here, hard and soft cheating. Hard cheating is actual exploits. Those are dupe bugs, getting to places you're not supposed to be able to get to, seeing things you can't see, teleporting, etc. Botting, on the other hand, isn't necessarily cheating, and it's defined as cheating by the terms of service. You violate your terms of service, but it's actually just legal inputs to the software. Now, the work that I was performing was a bot. It wasn't an exploit, so I'll be talking more about bots. Why do you want a bot? Well, World of Warcraft is really boring. There's this monster that appears every 10 minutes, and you have to run up, and you have to slash at it. It dies, it drops its gold, and you sit there and you grind and you grind and you grind. I have a day job. I can't compete with that 15-year-old kid who sits in front of his computer all day and his mommy comes in and feeds him dinner in his bedroom. I can't compete with him. That's why I want a bot. Just to cover the subject, though, there obviously are other types of bots. Aimbotting we already kind of talked about. And I did start kind of working with a PvP bot. In World of Warcraft, your position relative to the other character is very important in combat, so if you constantly stay behind them, you can win in a PvP battle. But you need an automated mechanism to do that because it's too hard to do by hand. So yeah, we talked about that. So there's a couple different ways bots work. Macros and scripts are the most common. Tools like AC Tool, Macro Machine, there's various other ones out there. They're very easy to write and they're very easy to understand because they their interface is completely at the level of the user. That is, clicking the button, sampling the pixel, doing things like that. They get a little bit more complex when you start reading and writing memory locations. For example, reading my location XYZ coordinates, reading these float values out of this certain offset in memory. DLL injection is the next stage, people injecting DLLs. This unfortunately is very easy to detect, so it's not exactly the best technique, and I'll show you a way we're going to get around that later in the presentation. And then finally, debugging. I did write a bot last year that was just a debugger that attached to WoW and was able to do a lot of stuff. So let's talk about macros for a second. They take over the entire graphical user interface. They inject keystrokes and mouse movements. You can't use the computer while it's running because it's actually driving the computer. And the feedback loop is typically either reading memory or sampling pixels. For example, you have a health bar, and if the red dot is here, you know you're at half health, things like that. So here's a little screenshot I took. This is one of my, incidentally, I've lost, at this point I've spent about $400 in banned accounts for World of Warcraft. This guy here, he's only level 7 in the screenshot. He made it to 55 before he got banned. And this is actually an AC tool script. It's very, very simple. You'll notice he's standing in front of a tent. The reason is I don't want any characters to be able to go behind him. He just stands there and the pile of virtual bodies start showing up. By the way, this exact script is available on rootkit. You can just download it out of my vault. Okay, so that's easy stuff. Let's talk about more complex stuff that's been done, process manipulation. A very common hack in World of Warcraft is called speed hacking. This is a form of client-side security. Because of performance reasons, you can't store everything on the server. The client's responsible for it. The most ridiculous thing is your XYZ coordinate. You can actually overwrite that in memory and instantly teleport to somewhere else in the world. That was one of the most common hacks in World of Warcraft for a long time. Some of the things I can do is I can control which way I'm facing by writing a vector into memory and my XYZ and whatnot. Here's an example of a program that does that. This is called Bubba's Warcraft hack, and you can see in the list there the various cheats that you can engage. For example, no fall damage. If you fall off a cliff, you don't take any damage. There's another one in here, lock speed, so you can run at a certain speed, etc. Now this is all invasive. There is another type of bot that you can write, which is a complete and total replacement for the client program. So I'm going to show you a screenshot of one of those. This is not released, by the way. This is something you can download. But here's the program running, and it's actually, it has a complete implementation of the protocol for World of Warcraft, so it's able to completely replace WOW.exe and run on its own. And this is very, very superior to in-game, but there's a lot more development involved to make this work. So just thought I'd throw that out there. Little map, it's a little map showing the X, Y coordinates of the various things. Now, this isn't an O-Day I found. Someone I know graciously let me put this in the slides for your benefit. This apparently still works. You can force any other player in World of Warcraft to sit down during PvP. So there's the message, and you just need to put their GUID in there, and you can force them to sit down. Moving on, thread hijacking is the technique that I originally explored when I was working with Jeremy, who wrote WoW Sharp. Now, WoWBot and WoW Sharp were a really popular botting program last year. So I'm going to describe how this works. We're going to hijack a thread, the main thread of the application, and we're going to force it to do other things for us, and then we're going to return it to its original location. Inside the program, World of Warcraft, for example, or any other client, are all the internal functions that do things like move, cast spells, pick things up. We can force the main thread to make those calls. By doing that, we don't have to have a macro anymore. We don't have to have any UI integration at all. We actually change the way the logic is working in the program. So here's how the original bot worked. Now, this is detected by Warden, so this is not the new stuff. We use Microsoft Detours, Detour Render World, which is called many, many times per second, and it detours into an injected DLL where processing takes place, such as forcing movement, casting spells, and then it returns back. Here's a screenshot of the actual bot program right here. It's written in C#. You can extend it in a variety of ways. You can go download this off the net today. Now, here comes the Warden. Originally, World of Warcraft didn't have this. They added this after they released the game. Warden, by the way, wasn't built originally for World of Warcraft. I believe it was also used in Diablo 2. In fact, if you disassemble the Warden, you'll actually see references to D2 client, things like that. So, the Warden works. It totally blew us out of the water. The problem is, we don't actually know what the Warden's going to do because it's downloaded off the server on the fly. So you have this fear of the unknown built into it. And they don't leave it on. They'll turn it on selectively for a weekend, ban 67,000 accounts, and then turn it off, and let it go for another couple of weeks, and then turn it on again. So you're kind of living in fear all the time of losing your account. The code can change at any time, and it scans memory and some other things. So I'm going to show you what I learned about it. First of all, it runs from the main thread. This is important. This is the key for my ability to actually get around the warden being able to detect me. I'll show that later in the slides, but at any rate, what it's going to do when a certain message comes in is it's going to go up here and find this injected DLL and this detour patch. It can scan memory and easily see that there's an integrity violation on the detour patch, as well as it can get all the DLLs out of memory and see that there's an injected DLL. Furthermore, it doesn't stop there. It scans all of memory inside the process. It grabs all the window text from all the open windows on your system. As well, it also opens up all the other processes and reads their memory. And it scans all that memory looking for botting programs and cheats. So let me show you a quick reverse engineering session that I did. How do you find the warden? How do you capture it? How do you even get to it in the first place? So inside of World of Warcraft, there's a class called netClient. In the netClient class, you can get down and find the receive. The receive will process packets, send them out. There's a type field in the packet. The type 2E8 is the one for the warden. It shoots off about every, I think, 15 seconds. Now, unfortunately, I had to redact my slides. As you know, Blizzard's rather aggressive about suing people. I don't want to be sued, so I did leave in just enough information, though, so you can see what's going on. Here's the call to receive. Okay, so this is where the packet arrives off the network. This isn't very hard to find on your own. Now, just a little ways down, you see we compare for the type, 2E8. That's the warden packet. And then you see the move warden entry down there. And then very shortly, you'll see a call through a pointer. That call through the pointer is going into the position-independent code that was pulled up into a memory page as it was pulled down from the server. And how do we even know it's called the warden? Because it says so. If you look, you can actually see the full strings, the full paths to all the different source code files actually embedded in the exe. So you can see that it's called warden client right there. Now, here's the dead listing for the warden. Again, I redacted this, but I'll leave in enough information so you can see what's going on. First of all, this slide is just pointing out the warden client looks like regular function code. You can see there we have a push EBP, and then at the bottom we have a regular return. So it's very easy to reverse engineer the warden. It doesn't have anything weird. Here's all the various calls. Here you can see the warden code that goes through local process memory and scans all the local process memory. Get current process, virtual query, etc. Here's the part of the warden client that reads and compares all the local loaded DLL names, looking for bad DLL names, names of DLLs that it knows belong to botting programs. Here it is going through all the external processes and comparing their names to a list of bad stuff. Now here's a really interesting one. It's actually opening and reading all the memory out of the processes, the other processes on your system. And then finally, and last but not least, here's the loop that goes through and enumerates all your windows and grabs all the window text. All right. So in response to this, you can download all the source code for this program off of rootkit. I just made a little program. It doesn't actually make the warden stop working, but it does report all of the activity that it's doing on your system. So the source code for this is kind of interesting, so you should go download that off of rootkit.com. So the question is this going to end cheating? Hell no. You can just turn off the warden maybe. The problem is the server expects a response, so you'll get disconnected. You could probably forge a warden, but I think that's iffy. I didn't try to do it myself. You got to understand, we don't really know what the warden's going to look for because we haven't received it yet, so how are we going to know what to do? How are we going to emulate that? If we had captured a known warden, we could probably forge a single warden, but we'd also have to have an additional routine that detects if the warden changes, and then you'll just disconnect if you have a changed warden. And you don't want to be the poor sap who has to keep up with all those new wardens. Okay, now let's talk about some real bots and the warden. There's a really neat bot called WowSharp. It was started development sometime in I think May of last year. It lasted probably about 6 months before it was completely and totally wiped off the map due to the warden. So this is an excellent example of using anti-malware technology and having it be successful. So there are programs that you can download that theoretically say, we can get around the warden, just run our program. But do you have any idea what it does? No. Do you trust it? Do you trust your character that you've been working on for 8 months to this little program? I don't think so. Here's another one, and it's just the bottom. It says, currently RB avoids every check in the warden client, making it undetectable. Whatever. Here's another one. Built-in randomization and completely external thread helps program stay discrete. Okay. This is an interesting program. This is called WOW Sniffer. It's actually just a totally standalone program. So that's another idea there, is you don't actually have to be in the process. You can just have something that's just watching the network. And that would be interesting, probably. So let me give you a short story. This is what happened to us when we wrote our WOW Sharp stuff. Again, let me preface, I didn't actually write WOW Sharp. I just worked on some of the evasion parts that were added on top. So Jeremy Coote wrote WOW Sharp. It started in January 2005 and went live in May. He spent about 4 months developing it. It was very, very cheap. It's like $2 a month to use it. And the way it would work is you'd log in and you get your offsets for the various things in the wow.exe client downloaded from his server on the fly. By September, he was dead in the water. And Jeremy did a little calculation and figured for all the work he spent, he probably made about $2 an hour for the whole thing. So he was moonlighting this business. It wasn't his day job. And the way that his process would work is if a new warden was detected, he would lock out the server so nobody could log in. This was to protect his clients so that he wouldn't get banned. The problem was a really hardcore warden came down that was detecting it, and the reverse engineering time was taking way too long, and all the people who had subscribed were getting antsy, and the pressure just started building and building. So this actually kind of caused, the straw that broke the camel's back kind of caused it to crack. I came involved in this way too late. I tried really hard to write a rootkit that would get around the warden, but the key to the success of this rootkit was memory cloaking. I didn't have memory cloaking working at the time, especially on dual core systems, and this was causing blue screens. I had a version that worked in my system, but Jeremy his couldn't work, and all the other developers got a version to test with that did not include the memory cloaking. We all got banned. Boom. And these guys were using their level 60 accounts to test it. I don't even know what they were thinking. So when this happened, we basically threw in the towel. But I, of course, kept working on it, but I just didn't have a lot of time. So what I'm going to present to you at the end of this presentation is really the next level of what we started back then. The source code to all of this is now available. He just put it all online. So now you can download this and make your own bot if you want. So in the end game, a lot of people did. They downloaded it. They make their own private versions. I understand that many people have undetectable bots today because they recompiled this and made it so that the banning hashes used by the warden can't detect this particular version. But the key is you don't release it, because if you do, someone at Blizzard's going to find out, and they're going to add that to their banning hashes. What did we learn? Number one, keep your bots private. And number two, the warden works. So here's what I began thinking. Well, what if we move the entire bot into ring 0? Sounds extreme, right? But one of the things I thought to myself is, I bet you Blizzard's not willing to go to ring 0 with their warden, because it's going to introduce potential instability in the system. They can't make that from a policy decision perspective. So if I do that, I can win, because they're not willing to go there, but I am. 4 million, 6.5 million players, I don't think they're going to have a kernel driver. Okay, I'm going to introduce the supervisor. Supervisor is a ring 0 program, and it has some interesting tricks. It's a full kernel implementation of what we're trying to do with WOW Sharp. So key features, no process. We don't have a running process on the system that has wow.exe. We don't have any injected DLLs. There are no injected threads. There are no detour patching. There's no debugger. There's no scannable memory. All the stuff the warden looks for, we don't have. So the technique I call shadow branching is going to use ring 0 technology to inject into the target memory a code page. And that code page is going to do all the botting for us. But in addition to that, when we hijack the thread, we're going to combine this code page with a memory cloaking capability that'll take it completely out of the user process memory. How many people here know what a page table is? All right, so you're thinking how I'm going to go down this road, I'm going to modify some page tables. Finally, in-memory, in-kernel TCP/IP stack, it's not using the existing TCP/IP stack, but rather it's using hooks into the Indus open blocks, so that it's like basically a TCP in the kernel on the side. For those of you who took the advanced rootkit training that Jamie and I gave on Monday and Tuesday, you've been given almost all of this technology. So for those of you who haven't taken the course yet, and if you really want to get your hands on this stuff, we give it all out in our training program. Okay, so here's the overall architecture. We have a botting application which is running on the controlling machine. This botting application is just a standard, regular Win32 app, and it has built into it a scripting language called Lua, L-U-A. This is the actual intelligence of the bot. It structures messages which are passed over the network and then read into the supervisor. The supervisor is running in ring 0 on the slave machine. In user mode, WOW.exe is running, and there's an implant. The implant is being cloaked. That's the part we have to cloak from the warden. The message will go to the implant will process that message, put the results back into the message will be copied back out in ring 0 and sent back to the botting application. So you can see this is you can see how the message flow will work. It's completely controlled from the botting application. So here's a summary of all the components. We have the botting application, which I call antifreeze.exe. This is still in prototype form. At the end of my slide presentation, I am going to show anybody in here who happens to work for Blizzard how to defeat all my stuff. So I figure by the time I get home, it's not going to work anyways. The supervisor.sys rootkit, the message structure itself, and then finally the implant, which is like a tiny little virtual machine kernel with bytecode that it can work with. So imagine it has its own little bytecodes that it works with. Okay, so shadow branching doesn't use a detour. What we're going to do instead is use a hardware breakpoint. Setting a user mode hardware breakpoint from the kernel is really, really hard. It took me a long time to figure out how to do it. So what we're going to do is we're going to hook the same exact location, render world, but without the detour. And furthermore, if the warden wants to detect if there's a hardware breakpoint, we might want to hook, I don't do this now, but we might want to hook PSP get context so that we can actually make sure it doesn't actually receive that information. Okay, and then we're going to use memory cloaking to protect the injected page. So here we go. Supervisor, when we hit the location in memory where we've got the breakpoint, supervisor will uncloak, jump to the injected payload. This is in the main thread. The injected payload will process the message, and then when it's done, in a single operation, we'll recloak the memory and hyperspace the thread back to its original location. To do this, we have to use the DR registers. So we'll use DR0 to set that breakpoint, and DR7 needs a flag set. Now, to do this for user mode, you understand, when you're in the kernel mode, you can't just set the DR, because that's a kernel mode context, and it's just going to get cleared. So there is a function call that Microsoft has in there that you're supposed to be able to use to set a thread's context called int_set_context_thread. The problem is it doesn't work. There's actually an enumerated type, context debug registers, where you're supposed to be able to set these registers. You can set them all you want. They never actually get set. The problem is when you actually try to set them, they don't work. So some reverse engineering needed to happen, and I figured out how to find the kernel trap frame. Now I'm going to show that to you on a diagram. If you can find the kernel trap frame, you can set anything you want, DR registers, EIP for the user mode thread. As soon as it transitions back into ring 3, all your context immediately becomes live. It lies at the bottom of the kernel mode stack. To find it though, don't trust the pointer that's in the ETHREAD block. It lies. Instead, you can use the initial stack pointer and do a calculation. And I think I actually show that here. FS0 to the KPCR, go down to the current thread pointer, find the K thread, follow the initial stack pointer, and then there's a calculation you can do right at the bottom, and you'll see that you can set the DR registers and other things there. This needs to be done using a kernel mode APC call. Now we're going to use it to control both EIP and the DR registers. Now we need to schedule a kernel mode APC to actually do the work for us. So I'm going to show you that. I think I'm going to show you that. No, I don't have the source code up. So every thread, you can schedule APCs. There's two kinds, kernel mode and user mode. The problem with user mode ones is if the thread's not in an alertable state, it won't actually execute it, but kernel mode APCs execute immediately. So we schedule the kernel mode APC with the information necessary to set the DR breakpoint. It goes live in the other thread. As soon as it's done, it sets a signal. We're waiting on it with whatever, blah, 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 over here. And when we kick out of it, now we're going forward again. So here we go. DR0, hardware breakpoint, render world, injected code page, back. And the warden code does not see any modification. In order for this to work, we have to hook two interrupts, interrupts 1 and 3. Interrupt 1 is a really neat one. It goes for single steps, branch trace instructions, ICE breakpoints, and hardware breakpoints. We're only going to use it for hardware breakpoints. And then we're going to use interrupt 3 as sort of a quote-unquote secret message channel, which I'll show you in just a moment, to communicate back and forth from the injected code. So we have to hook the debug interrupts. The problem with this is now you can't use WinBag or soft ice. You're out of the water because you can't have two debuggers on the system. So one of the things I had to do was develop a serial port console so that I could even debug my own driver, because I got really, really tired of trying to debug crash dumps. Each CPU has its own interrupt descriptor table, so we actually have to make a deferred procedure call to each of the processors in order to have all of the IDTs get hooked. So if you see this here, imagine each processor has its own IDT. Here's some source code. We initialize a DPC, and then we initialize an event that we're going to wait on. We can tell how many processors are on the system with KE query active processors. And then we can set the target processor for the DPC. This is how you force code to run on a particular CPU in the system. KE set target processor DPC, insert it in the queue. And we don't have to wait, but that's the way I designed it. So we're going to wait for the DPC to complete and then move forward. And we do that for all the processors on the system. Here's the DPC routine itself. This one's pretty straightforward. We unprotect memory using the CR0 trick, register CR0. We then hook the interrupt table and then reprotect the memory and set the event. Pretty straightforward. Okay, now what happens when an interrupt fires? When the interrupt goes off, at the top of the stack is what's called a trap frame, and this is the information that's in it. If you modify the EIP and IRET, you will hyperspace the thread to somewhere else. So this stuff is very important. Now, we can't do a whole lot of processing when we get an interrupt. We have to schedule a DPC, because what we don't want to do is hang around blocking up the computer. So whenever we want to do any sort of processing, we'll schedule a DPC, and then the DPC will take care of the work after this. Any modifications you make to the trap frame or the CPU context will be live when you return with an IRET. So this is how shadow branching works. There'll be an interrupt event on DR0 because we have a hardware breakpoint. The interrupt 1 will get called. Inside of interrupt 1, our ISR will uncloak the memory, will change the EIP in the context, and IRET, immediately hyperspacing the thread to a new location. And then when the new location is done executing, we'll have a secret code which causes an interrupt 3 event at the bottom. And what that will do is restore the same context back and IRET, immediately hyperspacing it back again. So it's based on 2 interrupts. We don't have to hook the page fault handler. Okay, so when interrupt 3, here's an example. Interrupt 3 fires, we get the trap frame, we save the EIP, we save all the information in the trap frame, and we also store all the information in the CPU off, because we have to restore all of it when we restore these contexts to hyperspace back. So we have to save that in a global structure. When the rootkit is done running, we get another interrupt 3 event, and we basically overwrite the trap frame with the previously saved data, as well as restore all the CPU context, and we're back. Here's an example of my structure that I use to store everything. You can see which items here are read from the processor directly and which ones have to be read from the trap frame. Now, you can actually send commands between the injected code and the supervisor via this trick. Basically, you hard code an interrupt 3, and you put some kind of secret value in the EAX register or something, and that's the code intending to tell the supervisor what to do next. That is like cloak and branch back, etc. The trick I was using for quite a while is to actually hard code some instructions directly after the interrupt 3, and those were read as a D word, so they actually aren't push pop, but when the interrupt fires, I actually read in direction of EIP and actually read this as a D word, and that's my secret code. I know it's obtuse, but it does work. And there's the code that does it. You can see I'm switching on it down there. A secret code equals, and then it has this secret code mentioned right there. Okay, so to return from the interrupt, we can tell which EIP throws the interrupt, so we can have behavior based upon that. When we return, we also need to make sure we set the RF bit. That's very important, or otherwise we'll end up in a recursive loop. I don't want that. So there's the whole hook. So when the interrupt fires, we disable interrupts. We call a routine called getContext that loads all the context up. We call to a debug handler that I've defined. You notice I push ESP on the stack, add 24. That's so that I have the trap frame pointing, I have a pointer to the trap frame as the main argument to the debug handler. Then when we're done, we set the RF flag. I've noticed some discrepancies in the documentation here. Just set it yourself, even if the documentation says you don't have to. Here's the routine that restores context. Gobbledygook. So total round trip. Interrupt fires, EIP points to the code we are branching. We uncloak the memory page. We change the EIP, causing the hyperspace. The new code runs. When the new code run is done, it fires again, an interrupt, and we return back with the original context. And there's the actual implementation of the shadow branching. You can see I'm copying the context in and out and uncloaking the page. Here's the code required to set the RF bit so that we don't loop infinitely. Okay, now how do we cloak the memory? It's very simple. We can go through the page tables and we can modify the physical address for a given page table entry and cause it to point somewhere else. The same virtual memory now points to entirely different actual memory. That's one way to do it. It's also very unstable. I actually have a second way to do it where we just copy the memory in and out of a holding pen, and that seems to work very well too. So page table manipulation, the way that I had originally done it is I allocated non-page pool memory, so I didn't have to worry about being paged out, and I used that physical address as the remapping point when I have the cloak in operation. There's an entire path of places we could, in theory, exploit the system. We could exploit the register that points to the page tables. We could exploit the page directories or the page tables themselves. We exploit the page table itself to point elsewhere in RAM. Here's an actual diagram of how it works for non-PIE systems. CR3 has the physical address of the page table. You can see the virtual address here. The top 10 bits index into the page directory. The next 10 bits index into the given page table. And finally, the byte index is in 4096 into the actual page of memory at the bottom. The way that Windows does it is they actually stick the base of the PDE at C0300000, so you don't actually have to, you just basically get the base address of that and you take your 10-bit index and multiply it by 4. There's a little pound define macro I made to do that. But you don't actually have to look at that. Well, you do if you want to check to make sure the page table is not paged out. But the actual page tables are based at C0000, so you can just go straight there and use the entire 20 bits and multiply it by 4 and find the page table entry you're looking for. Now, PIE systems are slightly different. I figured I'd cover that because my laptop happens to be PIE. I actually had to implement this. CR4 will have the following settings if PIE is enabled. It just has a slightly different system. It has up to 4 different page directories. You can see that on the slide there, the PDP, and then each of the page tables then go out. So it enables you to have basically the same virtual addressing system, but up to 64 gigs of physical memory now as opposed to 32. And so to look up, you don't actually have to go to that separate table again. It's just based in memory. You multiply by 8 because there are 64-bit entries in this case, and it's an 11-bit address. And the same deal with the C0000 page tables. Take the entire top 20 bits, multiply by 8, and go down. So this is the key right here. This code right here remaps the physical address to a new location. This is the code that actually does the memory cloak. Now, the problem with memory cloaking in this manner is that Windows maintains and performs an integrity check on the page tables when a process is shut down. So if I remap the page tables and the process dies, so what are we going to do about that? It's really lame, in fact. I thought page tables were really cool, and then when I thought of this, I was like, why did I go to all that work? This system, this new idea I had, was to simply make a 4K memory in non-page pool as called a holding pen, and when we need to cloak, we overwrite A's all over the memory in user mode, and then when we uncloak, we copy the holding pen over the memory. When we recloak, we copy it back and write the A's back again, so we just move it. And this is very dependable because it doesn't require any changes to the page tables at all. Here's a small sequence chart showing how it works. We allocate the memory, supervisor allocates the memory, puts it into user mode. When there's a cloak, we move it to the holding pen and then fill the user mode memory with A's, and then if there's an uncloak, we move it back again. Simple. Here's an example of it. I have my serial port console to my rootkit running in the screen on the side. First, the test program prints actual memory. Then the next, I cloak that memory address. You can see down there on the prompt, I type cloak in the actual address. You can see now they're all A's, and then I uncloaked it. All right, so that's the memory cloaking. Now the implant. This is the thing that goes into the World of Warcraft client. This is the code that's actually injected. How does it work? Well, first of all, it's position-independent code, similar to shellcode. It's, when it loads, it'll parse the PE headers of all the loaded modules, and it will load up all the function pointers for a set of functions that you need to use. It subsequently loads this table of function pointers up and puts it into its own memory space. It then sets up its own memory page to be cloaked using one of our quote-unquote secret messages. And then it sets up the function, the detour hook on the render world call. And then finally, it's the code that actually executes the little microkernel for the messages. It's written entirely in C, so I have a weird little fusion system I came up with for writing so I don't have to hand code the assembly. There's a format for this. There's a header and a loader portion, and then there's the hooking code, and then at the bottom is all the data. So those are all my function pointers and strings and things that I need. It's very precise and parsable. And I actually have an example of it. The data has, for example, for functions, it has a DLL name followed by a special character and a null, then a series of function names that you want to load, followed by a null, next DLL, etc., up until the point you don't need any more of those. Double null, now all your data strings, and then double null. Here's an example of that. That's the actual source code. Here I'm loading up output debug strings, sleep, strlen, some other things. The actual main, quote-unquote, main function call inside of the, and remember, we're writing this as C, receives a pointer called MFT. That points to the actual data block. So this will get called, and the data block will be all fixed up with all the function pointers. So the nice thing about this, even though you can see I'm doing some inline assembly, you'll also notice that I have local variables. I can actually call functions and write the code similar to the way I'd write C. I can actually add additional functions, and when this compiles, it actually poops out just a giant hex blob that I can cut and paste into my injection code. There it is. So that's called my quote-unquote shellcode compiler, and we gave that out in our advanced rootkit class earlier this week. Okay, so we allocate the memory, we inject that blob that you saw, we branch to it. As soon as the blob is done, we cloak it by moving it into the holding pen, and when our hook fires on render world, we're going to do the same thing all over again, uncloak, move it back, branch to it. When it's done, it recloaks, and the process just repeats forever. This is the code running. Those A's are not real. There's code right there, and it's executing right now. So there you can see the memory cloaking with the shadow branching working flawlessly. So, the only thing we do now is once we've got this working is we force in-game events. So we know where the locations of all the various functions are inside of World of Warcraft for casting spells, moving to a location, picking up all items from an inventory, etc. There's probably about, I think, 9 functions that are used in this manner. All we do is the injected code will force a call against one of those functions to get something to happen, say casting a spell. And then when it returns, it'll return back to the main thread. You can also do things in the chat window and other things like that with the same system. Okay, this is the complex slide, I understand, but this is the entire thing. So here comes the main thread, render world, hardware breakpoint, uncloak, jump to the injected code page. The injected code page reads from the message what it needs to do, and it proxies the function call, the cast spell by ID, script execute, clear target, etc. Then returns, recloaking, and restores back to render world. Warden didn't see us. This is the remote window that drives it. We call it antifreeze, and it has the scripting language under the hood. It uses Lua. It uses supervisor on the remote system. And in theory, if I don't release it, I don't expect it to be banned by Warden. Now, how would we make a better Warden client? Let's look at the other side of it. First of all, going to ring 0, but as we talked about earlier, that might not be within the policy for Blizzard. However, we know Punkbuster goes to ring 0, and they detect a lot of cheaters. Really, really good tricks for detecting ring 0 code, even without having ring 0 code. Do things with timing to see if you're being debugged. Scan the stack. You just saw I called cast spell by ID. If somewhere down inside cast spell by ID, it scans back on the stack and sees that it wasn't called from the location that it thinks it was, that is, the return address isn't set to the one it thinks it should be, you could use that as an anomaly detection. Furthermore, while we're calling those functions, remember we're in an uncloaked state. So if you could somehow randomly branch to the Warden from a non-predictable location, that might cause a lot of problems. Of course, we can solve all those problems, but it just makes a lot more work for us. Another thing to do, and this would work really well, if the Warden does different games with exceptions, chances are my rootkit is going to fault up what the expected exception chain is, and they're going to be able to detect it. And finally, and this one's just so brain dead simple, just use the DR registers for something important that they have to be there. Now I can't use them for my shadow branching, because I would mess up whatever's already there. So this is kind of my concept for the better Warden. It's called Fear of the Unknown. This is basically what they have. Update at any time, require a positive response, scanning for stuff you know should be there, and then scan for stuff you know shouldn't be there, and put the entire go, no-go decision on the server. Disseminate multiple versions of this per account. So the version of Warden that I have isn't the same one that you have, so even if I reverse engineer mine, it's not going to help you. The theory being REs can't get their hands on all the versions. There are some other applications of this technology. I think that rootkit technology, such as like the supervisor, can actually be used to watch a system that you think has been compromised. Now here's an application to security that has nothing to do with Warcraft. If you can covertly monitor a system and the malware and tools that are on there can't tell that you're doing that, whether you're doing that through a rootkit-like technology or a hypervisor layer, this is actually an application that would allow you to catch bad guys. One idea that I have here is something called active forensics. Instead of looking at just a hard drive, you could actually collect runtime data from a system as it's being used, perhaps by an attacker. An example, let's say they have an encrypted command and control channel, and you want to get the decrypted packets. Obviously they're going to get decrypted, but they're going to be decrypted in memory and pass to some function. Put a breakpoint there and sniff them out of memory. You have the decrypted packet stream. It's just one example. Just some notes on that. Corporate espionage now outranks malware as the #1 security concern in the enterprise, according to an analyst firm. And according to the FBI, $250 billion a year being lost in espionage. And our good friend John Pescatori says, yes, there is a role for stealth in the enterprise world. So my hope is that maybe some of this rootkit technology can be used for good to catch bad guys. This is an upcoming book Gary McGraw and I are writing. We're going to try to get away with putting as much as we can in here without being sued by Blizzard, but we'll see. And it'll, of course, include much more detailed information on all things I just showed you. I got done about 10 minutes. I got done quite a bit early. Are there any questions? Yes, sir.
You said that when the Warden runs, it grabs input text from other windows on currently running the system when it runs?
Yes.
Is it possible they try to have a document open with personal or classified information as far as my company's concerned, or the Warden text that won't cut out the filter?
The question was, if you have an application open with potentially sensitive information, will the Warden read it and will the Warden send that back to Blizzard? The answer to the question is, first, yes, it will read it, but no, it won't mail it back to Blizzard. The way the Warden works is it actually hashes the strings and compares them against a set of what are called banning hashes. So no personal data actually gets sent back to Blizzard as far as I know. Yes, sir. The question was, will hardware virtualization change this whole thing? I could imagine writing a bot for the hypervisor. That would be really cool. That would be really, really neat. And it would be really difficult for Warden to detect that. Okay, thank you very much.